Hello. Wenbin, can you hear me?
Yes, I can hear you.
Hold on a second, I can't hear you. Can you guys hear me?
Yeah, you are audible.
Okay.
Yes, yeah.
Apologies in advance. I have the flu. Took a lot of medicine to feel good enough to present.
Professor, I guess we cannot hear you.
We cannot hear. We cannot hear you.
Yeah, there is no audio from your side. Mm,
From
no,
the
your
professor?
mic is not on your mute, but we cannot hear you properly. There is no audio, none.
Hello? Can you hear me now?
Yeah, yeah.
Okay,
Yes.
thank you. So I was mentioning, so I will ask first if someone really wants to go first. If not, I will go by order of topic number uh, to to have you present. So is there someone who would like to present first?
Professor, hi, I am Parth. I have mailed you regarding my situation. So there is a 2-day conference in another subject.
I understand. Yes, there is
Yeah,
someone else who also asked me about this.
yeah.
So
So will it be all right if I submit my recorded video and PPT along with the term paper submission?
yes, it will be okay, and I will post it on the site so everyone can see your presentation in so on the Brightspace
Okay.
when you have submitted it. Okay.
Okay, okay. I'll submit it by the term paper submission deadline, 8 December. Is that all right?
Yes, yes. No, I
Yeah.
understand today was a day of conference. People who had the has geohazards
Yeah,
class will have will have had a very busy day today.
yeah. So sorry for the inconvenience.
No problem, no problem.
Thank you for.
So other than that, someone no, nobody wants to. So I will go by. If you are not here, don't worry, because I know that someone else has the presentation. So I may just. I'm not sure exactly who has which presentation. What was your topic, by the way?
For me,
Yes.
yeah, it's the 12th one. Formulation
Okay.
of
Was there
flow of.
someone with you?
Uh, I'm not sure. Yeah, in the project tab there is another person, but I have not contacted with him.
Okay, you were not
So
able to
yeah,
communicate. Okay.
so I'm gonna be like presenting and preparing my slide on my own.
Okay. Okay. We will see who is here today then. So if I believe topic 3 is the other presenter who is not here today, right? Yes. Okay. So in terms of presentation then, can we go with topic 7, which was Wang Jianghao, I believe, was presenting. Are you able to present today?
I can go first.
Okay, you can go first.
Yeah.
Okay.
Just
Your
give me like,
topic is,
I think 10.
oh, topic 10. Perfect.
Okay.
Okay. In that case, oh, just give me 1 second that I start something that I need to monitor situation while presentations are going on. Da, da, da. Okay. Oh, sorry. Okay, so you may proceed whenever you are ready.
Just wanna hide the. Okay. So my presentation topic is number 10, which is a THM formulation. My topic that I decided to do my project on is a semi-implicit operator split THM solver for freestyle settlement, based off of some of the research that I do on the Hudson Bay Railway. So some of the goals that I have for this project is to describe THM numerical formulations in geotechnical engineering through a case study using electric resistivity tomography as an initial condition. I want to use the finite difference method on a heterogeneous soil to couple thermal hydraulic behavior. I'm going to apply thermal hydraulic hydrodynamic behavior to mechanical coupling. and explore how freeze-thaw-induced changes in hydraulic conductivity feedback on plume migration, and identify where thermal impacts are the strongest. My take in THM for geotechnics is that, well, hydrodynamics from a fluid perspective means the motion of fluids and not necessarily a fixed soil characteristic. So how do I address this? So first I want to talk a little bit about my conceptual model. So I guess before I start I can talk about this. What we see, this little map on the right, is a resistivity map of subsurface near the railway embankment. And so what we want to do is create a numerical model of a proximal terrain unit that is parallel to a peat plateau and a fen next to the HBR. When you use subsurface terrain resistivity to model THM evolution using this image right here and the reported soil stratigraphy, and infer and apply constant head to simulate wetland behavior without the transient hydrological inputs, apply dual drainage, and then model seepage, thermal and mechanical effects with background freeze-thaw settlement and seepage, and then couple it. So how do we do this with limited data? How do we get started? So the first thing is to apply a fixed grid and like superimpose it over the image, determine the terrain profile, and then map that onto the fixed grid. But before we get too deep into this, what is THM and why is it so complicated? Well, THM really, in terms of coupling, it must occur, like the coupling, regardless of how complex it is, for it to be fully coupled, it must be within the same time step. So, we have a lot of parameters here. We can have, multi-field coupling, thermal coupling, hydrologic, mechanical processes, which are all independent. Each GDE, it can be second order, first order, whatever you want, and it's coupled with nonlinear terms. We have multi-scale physics with different time scales, and then in terms of different THM approaches, we can have implicit finite elements and finite difference methods. We can have explicit methods. We can have particle, like material point method, which somebody else will talk about today. And then for THM, we have multi-dimensional behavior, such as 1D, 2D, and 3D. So today I'm only going to talk about 2D. But the one thing I want to draw your attention to is that THM can be hydraulics, can be thermal, can be mechanical. And my approach to looking at this problem is to kind of build it one coupling step at a time to produce a fully coupled finite difference model. But at the end of the day, THM is energy, water, and stresses. So the governing differential equations, the GDEs that I used saturated conditions, so I used Darcy's equation. For the thermal equations, I used advection and conduction. I used advection and diffusion. And for the mechanical component, I did 1D soil columns where we looked at strains, pore water, settlement, and stresses. So the boundary and initial conditions, here is an example of a soil column extracted from the sites, which is, we have organics, silty marine clays, and sandy till. The organic would be peat with a very, very low density. So the boundary conditions, we use dual drainage. In terms of the thermal boundary conditions, we use the thermal penetration wave as both an initial condition and the boundary condition. I call it a boundary condition because at the surface of the soil layer, the thermal penetrating wave, once it hits the surface, it then, propagates through the soil. So at time 0, it would just be the initial state. And then the same for advection diffusion, where at time 0, if there is no input source, it would just be 0. And then mechanical, it's fixed displacement with a free surface. And I do want to talk about Archie's law, because in geophysics, one method to relate resistivity to water saturation is using Archie's law. And there's some parameters here with some suggested best practices. But at the end of the day, once you compute all this and you apply residual water content, you can compute the effective saturation. So the numerical setup, this is the meat of the numerical model. So we have an initialization phase, an outer step, and then an inner step. So the way this works is in the outer step, so we have our initial step, and I guess I can go through this a little bit slower, but I just want to explain this diagram really quickly. But so we have our geothermal gradient, or our temperature penetrating wave, which defines the thermal state of the, I guess, the 2D mass. Then we have our implicit hydraulics, and then we apply advection diffusion. This plays into the mechanical, where we look at the suction head temperature and pore water, and then we iterate. And then we have other diagnostics. So how do we build this? Well, one, build a 2D map. So to do this, we import our inputs, read the ERT mask, define the grids, define the time discretization. So time discretization, this was very challenging because the larger the time scale, the more computationally intensive it gets. I chose 5 days. I think that was something that was reasonable for this model. Then apply the property field inputs. So we classify the soil layers, apply the terrain surface from the ERT mask. The most important part here is to store the initial state variables. So once we have the effective saturation, then we can apply all the other variables like the hydraulic conductivities, geothermal temperatures, the initial head, and then we can derive the porosity. In this case, we did have the unit weight, but then we can find the initial effective stress and then settlement field, which at time 0 would be 0. I didn't really make a slide on this, but the approach here is to use the Van Genuchten approach with the soil water retention curve, because this feeds into the soil freezing characteristic curve, which is based off the latent heat of fusion, which is the energy, which is I think 330 kilojoules per kilogram, which is the energy needed to change the phase from ice to water or water to ice. So once we start computing the outer steps, we look at the seasonal surface temperature, we apply to the top boundary, we allow the penetrating wave to penetrate. This sets the freeze-thaw state, driving the initial temperature changes. This step is extremely crucial because when we have, and I'm going to go back here for a second so that this makes a little bit more sense. When we have our penetrating wave, it's a periodic function, and so depending on where you start kind of governs where you are within the period. So why do I bring this up? Because depending on what your initial temperature is across the depth and I guess the width of the two-dimensional space, in conjunction with the saturation, it will then dictate the frozen and unfrozen fraction. This is extremely important for the no-flow boundaries or the partial flow boundaries. So this is why I say this sets the freeze-thaw state, because whether it's fully saturated or partially saturated, we then bring in ice content into the mix, which gets a little bit complicated. So another component of the outer time step, as I mentioned, is the Gaussian plume. For simplicity, I added a plume source at x0, z0 for one of the examples. For the actual model, I used the temperature at near surface and applied it to the hydraulic head, and then that in and of itself acts as a thermal plume seeping into the ground. This thermal plume is computed based off the fact that we compute the Darcy velocities. So once the Darcy velocities are computed, we then have the plume following the seepage paths and then dissipating heat using a Gaussian distribution. So here it is again. So then because we have nonlinear terms in the implicit hydraulic step, what we want to do is do an inner Picard loop. So we start with our initial conditions. We guess in terms of the plume concentration, we have a porosity, we have our head. We also use a fixed time trumpet curve to compute the freezing, to define how much pore space is water and ice, compute the conductivities. And so once we get into the inner loop, sorry, one sec, my slides are a bit messed up. So once we get inside our inner loop, we converge, I think it was 6 iterations. I think I wrote that down here somewhere. One second. Yeah, so so for the inner loop, we then resolve the nonlinear parameters imposed by the hydraulics, and basically the way the inner loop works is because the hydraulics itself. So to compute the explicit part, we use the initial k, and then we propagate that throughout the fixed grid. Once we propagate that through the fixed grid, what happens is we're not going back and updating k. So then we do need to converge on the other properties that we computed. And so that's where we update porosity, compute pore pressure, compute total and effective stress, compute volumetric strains, and recompute void ratio, gamma dry, gamma state. And for diagnostics, I looked at the critical hydraulic gradient between each cell. And so for numerical stability for the explicit portions of the THM formulation, I looked at the CFL, I looked at the Fourier number for the dispersion, and I looked at the residual water content and then factor of safety against piping. So now that we have all this, let's get into building this THM. This is the fun part. So I wanted to show you guys a little bit of how we can transform what we did in class with the sheet pile example into a thermal hydraulic problem. So when I was talking to you guys about the thermal penetrating wave, the thermal penetrating wave, using its extremities for the wave function, we get this seasonal trumpet curve. And that's what we see on the right. Now, what we see on the left here is a GIF of a thermal plume injection of, I believe, 15 GPM at 8 degrees Celsius. Now, what we can see here, and mind you, the sheet pile is just a no-flow boundary. So we kind of, just for sake of argument, assume that it's filled with soil. Now we see how when we inject when we inject 15 GPM at 8 degrees Celsius, we can see how the plume propagates as the soil freezes and thaws. Now, what exactly is missing? Well, look, the seepage field is static, so how do we fix this? Well, we had a dynamic seepage field. And so the reason why the dynamic seepage field is so important is because our no-flow boundary, so we started off with dual drainage, for example, and it transforms into a situation where you have no flow due to freezing. And so as it relates to the terrain mask, this is actually what's happening in the example that I was using for this paper, or for this project. We can see the seepage fields evolve with depth over time, and we can see that there's the near surface soil layer, the peat layer, the silty layer, and I think it was, or sorry, the marine clay layer and the silty layer. And we can see how each layer responds differently over time as it freezes. Now, one of the issues I had when I was building this was that I probably should have used material point method to better represent the large model strains. But for a finite difference example, what I decided to do was represent the settlement and the change in effective stress using a color map. And so this is kind of how I showed the outputs. So one of the questions I had going into this THM formulation was to understand the effective heat fraction and its impact on the heat transfer in the soil. So how much do thermal plumes impact freeze thaw versus just conduction? And what I found here is the near surface, or the active layer, is actually dominated, as we can see by this chart, it's actually dominated by diffusive effects, while when we are in a fully warm season or fully cold season, it's dominated by conductive behaviors. And so one of the reasons why, again, I wanted to do the THM project is to also integrate geohazards into this. And as we can see by this map, this is the minimum factor of safety against piping. So as we have our THM solution, and we have freeze thaw, and we have seepage, and all of these THM effects, at the end of the day, using the fixed grid finite difference method, I was able to calculate the hydraulic gradient and the critical hydraulic gradient between each neighbor and figure out, okay, what are the most susceptible paths? And here, this could be useful for determining, the emergence of talcs, sinkholes, and so on. So based off this, how do we calibrate it? Now, the calibration kind of goes beyond the scope of the THM formulation, but I kind of classified this between numerical calibration, measured calibration, so different parameters we can calibrate and tweak, and then physical calibration, for example, like hydraulic conductivity, Van Newton parameters, and so on. And so if I wanted to calibrate Van Newton, well, this is just one example workflow, how we could iterate through calibrating a model. So I know my code doesn't really fit in this paragraph, but yeah, that's my project, and thanks for listening.
Thank you very much. So you went the extra mile there making all these simulations. Congratulations. Does anyone have a question for Perry? We'll try to keep it short, but what was the time step that you ended up choosing there?
5 days.
5 days? Okay.
It's not appropriate, I'm going to be honest. I think the appropriate time step should be 12 hours. But it's, so when you look at any type of model, you have to balance I guess your spin up time, right? How far back do you go? How far in the future do you go? And so I valued a longer runtime than a shorter but finer runtime, because I wanted the model to evolve more so I could see how it behaved instead of having a short model that behaved perfectly. I wanted to see multiple freeze thaw cycles. So the idea for me was to get 3 years, about 1,000 days. Um, if I did 12 hours, I would not even get a whole year.
Okay. So, any other questions?
Harry, hello. Can you hear me?
Yeah, I can hear you.
Yeah, I want to see your CFL conditions
Yeah.
because I will talk a little bit about this in the material point method.
Yeah, just one sec. Um, oh, let's see. Have to find the slide. It's right here. Okay. Alright. Am I showing you the right? Oh, not showing you the right one. There you go. Yeah. So CFL is based off of this one right here. So there's different, I guess. So that's actually yeah. Just take a look at it.
Yes,
And
it's
look,
different.
yeah. So CFL it can apply to different like when you do finite difference, it really applies to whatever you're modeling. For example, like I have a Fourier number here. Fourier number is very similar to CFL. It's just for diffusion. Yeah, it's kind of like the idea of like averaging your nearest neighbors based off of whatever behavior you're trying to model, so that you maintain a stable solution. And I guess as like a rule or as something that you kind of have to converge to, you kind of just set some sort of tolerance, some sort of rule, and you just converge until you meet that.
So you use this CFL condition to define the delta x or delta t.
Like it doesn't define like delta x or delta t. Here. So if we look at our outer step, right? Once you compute the thermal, the hydraulic, and the mechanical, right? Or say just do thermal. The solution that you so kind of what we learned in class. When you do explicit, your solution might not be correct until you start to converge. And so what we were doing in class is we were looking at the nearest neighbors and we were converging until something, right? So what exactly is the appropriate limit of convergence? And that's where you apply the CFL number.
Okay, I see.
And so here for convergence checks, there's, head, porosity. I used a bunch of them because overall, and this is what makes THM so complicated, is I think in this model there's 28 parameters. And so the parameters, so depending on, hold on, I'm just going to stop sharing for a second. Depending on what you're modeling, or what your output is, that has to converge, your parameters have to converge. It's not just, if I compute hydraulic head, for whatever reason, or say we're doing a seepage field, right? It's not just the seepage field has to converge. All of the parameters within the field have to match because you compute everything. And so in my approach, that's why I store the initial state variables, and then I update the state variables.
Got it.
So one of the things that helped me here, and Professor, I love Google Collab, is that I have a very large Google Drive folder. I start with my initial state. After I have my initial my CSV with my initial states, I have maybe like 24 columns. Then I compute everything, a new output, and then every time step, I just add new entries, and then test if they converge. If they don't, then what I did is I just overwrite them until convergence, and then I have a diagnostic output which checks it for me. Yeah. So
I see. Very good.
I hope you guys enjoyed that. I spent a lot of time on it, and I still get confused by it. It's one of those tricky topics, but yeah, thanks.
Thank you very much.
Thank you.
There are no other questions, and we'll move along. Who will do the? So we have maybe we have Wenbin and Shaori.
Yeah, I
You
can.
have you made a combined presentation?
I know I just make the presentation by myself.
Okay.
Yeah.
Okay. Let me just adjust my da, 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 da. Uh, oh, just sorry. Give me a sec. I'm just reorganizing my sheet here. Okay. Um, so you want to go next then, Wenmin?
Yes, yes.
Okay. Please.
So I share my screen now.
Yes. Whenever you're
Okay.
ready, go ahead and share your screen.
Okay. My topic is analysis of slough stability using the material point method. And I want to introduce the development of the NPM. Actually, it is developed based on the PIC, particle in cell, which has the philosophy of particle to background grid and grid background grid to particle seizure. And but it is used for the fluid field. And for the slope, we have soil material. It is like something like time dependence. So after consider this time dependence effect, here we have the NPM. Then, based on the NPM, for the slough stability analysis and the other geotechnic engineering application, the GIMP, Generalized Interpolation Material Point, is a framework developed for the engineering use in the practice. It can do some land size simulation, like other things like crack development analysis, and also it can get the safety factor according to the strength reduction method, etc. And the GIMP can be also developed to a very more accurate model called the CPDI. It is considering a deformable domain. The GIMP's domain is a fixed domain, and the CPDI consider a deformable domain that is a little bit complex, but it is more accurate. In my study, I just want to focus on this GIMP framework because it is very easy for us to use. Okay, let's go with the NPM theory. The NPM theory starts with the conservation of the momentum, and this is the equation, and you consider a text function, which we can say also a virtual displacement in multiple disks, and do the integration, and use the green theorem and the Gaussian divergence theorem. You can get this energy equation. Then we need to consider the particle properties and how we map the particle properties to the background grid. The particle properties is based on the characteristic function of a particle showing here. And according to this, you can get the property distribution in particle. Then you consider the shape function. You can map the particle property to the background grid. According to this, the energy equation will become this more longer equation. And we assume the weighting function expressed in this way and the gradient weighting function expressed in here. And also consider the duration of the momentum here and also the internal force and external force. Then this long equation can be changed into this simple form. Also, we need to consider the constitutive model because the soil is have the elastic zone and plastic zone, and so we need to expand a little bit in this concept. First, we need to find the total strain rate. It is used for the updates in the strain later on. Then, because we are dealing with the large deformation problem, we consider the German stress rate, and this is for the elastic. Then we need to have the yielding criterion. For me, in this study case, I use the Drucker-Pryor yielding criterion because it's simple, I think. And F it is expressed in this way, and if the F is less or equal to 0, the material is elastic. And if the F is larger than 0, the material is yielding. And if the material is yielding, we need to update our stress based on this plastic stress rate, showing this here. Then we have that basic theory. We can go to our GIMP. When I introduce the GIMP framework, I want to also introduce a case study to make the explanation more clear. The case study, we have a slope and have this geometry and this material properties, and we have a horizontal fixed boundary condition at the left and right of the boundary of the slope. And at the bottom of the slope, we have a horizontal fixed and vertical fixed boundary conditions. Okay, the step one of the GIMP is the initialization. There's a two way for you to do the initialization. First way, you can do the final element analysis first, and you create the initial stress field according to the output of the FEM. You can extract the node location information and also the corresponding stress to the NPM model. Or you can just initial the stress field with 0, and then you apply the weight, then wait until it reaches balance. After this, you need to generate the background grid. In this step, it's very important for you to define the mass density of your grid, like dx here. You can use the mesh study to find the best dx. And step 3, you need to determine the weighting and gradient weighting function as shown before. The weighting function in GIMP can be very simple. You can um, it is given by the overlap area, which is the yellow part in these figures, divided by the volume of the particle. And for the gradient weighting function, it is expressed in this way. It is the difference between the center of the overlap area and the location of the particle times the weighting function divided by the dx cube over 12. Next step is to determine the nodal mass and the momentum. The nodal mass and momentum at time k is given by these two equations. Then you need to update the string. Actually, it is just use something like finance difference, and you can just calculate the string increments by by multiplied by your time step. Step 6 is to calculate the stress increment. If the material is in elastic zone, you can update the stress by the German stress rate. And you have the elastic stress rate, you can need to put it into the check. If the material is yielding, you need to update your stress with this plastic stress rate. Then you need to update the internal force according to the stress. Then also the external force according to this is the body force and the traction. And now you can update the velocity according to the internal and external force. Then you can also update the position according to the velocity. And the last thing you need to update is the density. It is start with the conservation of mass, and you follow these steps, you can get this function to update the density of your model. The final step is you need to repeat step 4 to step 9 until the time reach the total time we define at the very beginning of the analysis. This is the whole GIMP framework, but we still have 4 things that need to figure out. First thing is how can we define our time step? The second is how can we apply our boundary condition, and how can we apply the loading and how to trigger the landslide. To define the time step, we know if the time step is too large, the output will be very unstable. So we use the CFL conditions, and we can get this stable time step. This is LP here is the length of the particle. Then how to apply the boundary conditions. In GIMP, if you want to fix the particle in X or and Y direction, you just set its velocity equal to 0. So it will make the particle does not move. So it will like something like a fixed effect. The first thing is how can we apply the loading? If we apply the loading within one time step, oscillation will be occurs in our outcome. So we need to have a damping loading scheme. Firstly, you need to gradually apply the loading within several time steps. Then you should update the velocity with the damping. Damping is theta here, and we also often use it equal to 0.01 as default. And issue number 4, how can we trigger the landslide? The trigger of the landslide based on how you initialize the stress field. If you initial with the zero stress field, you just wait for the moment reach the balance and then you gradually reduce the cohesion of the soil to 0. Or you just can initiate the stress field with an unstable stress field and you gradually apply the weight and wait for the landslides occurs. Then you can get this fantastic landslide simulation. But for our engineer, we are more interesting in the safety factor. And how can we get the safety factor based on NPM? Actually, it is borrowing the idea from the strength reduction method. First, we need to define a reduction factor, and we also need to define a failure criterion. Then we have this reduction factor, you can reduce the cohesion and the friction angle of the soil, and you run the NPM and check if the outcome meets the failure criterion. If it's not, you need to redefine a new reduction factor and run the NPM again and check again. If the output meets the criterion, the safety factor is equal to your newest reduction factor. In our study case, I slightly increased the C5 value here, and my criterion is the maximum displacement of the slope top. And I generate these figures, which is the reduction factor versus the maximum displacement. And we can see displacement jump in this point. So we can say this loop have this 1.06 safety factor. According to the introduction, we can draw this conclusion. First, the material point methods can solve the slope stability analysis first, and with the particle to grid and grid to particle philosophy, it is very efficiency to deal with the large deformation problem, which the finite element methods cannot do very well. And by borrowing the idea from the SRM, strength reduction method, we can get our safety factor based on NPM. And NPM also have the broad application prospect in geotechnical engineering. Future study can be done with develop more accurate algorithm and do with more type of analysis like coupling analysis and dynamic analysis and so on. This is the references for my study, and thank you for listening. Any questions?
Thank you very much. It was very interesting. Any questions?
I have a question. So the basis behind NPM really it's Green's theorem, and so it's essentially what happens once you have some sort of shape, or I guess the question I want to ask really is, does the particle size influence the I don't know
The outcome?
yeah.
Yes, the particle size will influence the outcomes. I think
And
so. Because in my practice, I try so many different size of the particle size,
yeah.
and I find there's some size of if you set it larger or smaller, it will give you different outcomes.
Yeah.
And I just find particle size that I try a lot and find the best particle size that the outcome will exactly what I expect.
Mm-hmm. Okay. And what was the selected particle size in the end?
Actually, it is in my oh, I need to share my screen. I write on my screen on my slides. It's in for my study case, it is yeah, here. The volume of the particle is equal to 2 dx squared,
Okay.
and dx is the distance between the neighboring nodes.
Yeah.
Yeah, this is I think it's the optimal for my study case.
Okay. Yeah, that makes sense. So yeah.
Any other questions? I do have one question. You found the factor of safety for that slope. Did you compare that factor of safety you found with the factor of safety you would get for the same slope using, the standard software like Slope W or IRCAN or something like that, that use the standard method of slices or something like that? Just to have a benchmark, do you get a similar result or not?
It didn't do this, but I can share you with
It's always
a
good
paper.
whenever you do these kinds of studies. So you know that is a standard method, and you say,
Yeah,
well, we
yeah,
can do it also using this method. It's always a good idea to go and say, see if we do it this way, and does it compare well, or does it give you something that's very different, right? Because we can see
yes, yes, I agree.
from your test that we do get a value for a factor of safety, and that's perfect. But the next question you should always ask yourself is, how does it compare with the standard approach that gives me a factor of safety, right? Because if you find that it gives you something very different, then questions come up, right?
Yeah,
So,
yeah, yeah. Yeah, I
eh,
totally agree. That's a good suggestion.
okay.
I actually have another question.
Oh, go ahead.
So you said you computed weight factors, right?
The weighting function.
Yeah. So um, so the weighting function. Uh, I guess can you just explain just quickly the weighting function again, like what it does?
Actually, it is something like this weighting function is equal to 1 for the location is exactly on what you target on. It is
So
like the summation of
so at one point you were saying you essentially iterate the weighting function until it meets your criterion, right? But the
yeah.
question I have is, does the iteration on the weighting function impact
Oh,
the
really?
factor of safety?
Yes, yes.
Okay.
Uh, Actually, I mentioned this CPDI here. In this paper, it has a more accurate weighting function and the other setting, and it will give you a more accurate result theoretically.
Mm-hmm.
And but for GIMP, we can only use this single way to get the approximate results.
Okay.
And this is for engineering use, I think is enough. But for study, you can use a more accurate model, but this model will be more complex.
Mm-hmm.
Yeah.
Okay. Thanks.
Yes.
Sorry. Thank you. Um,
Okay.
so I believe for tonight we will have potentially one more presentation. If from Shaori, do you have a presentation for us tonight?
Yes, I can I can do my
Okay,
presentation.
it will be the last one for tonight, and all the presentations that have to be presented will be submitted via video, and I will be posting them on Brightspace so everyone can share everyone else's presentations. Okay, let me just give me a few seconds to set this up. Oh, so you also have topic 14, correct?
Yeah.
Okay.
So I can start.
Give me one little second.
Okay.
Uh,
And I'm very sorry, my camera is broken, so I can't
oh,
open
okay.
my video. I'm sorry for that.
Okay, yeah, that is the risk we take when we do but at least you have your presentation, right?
Mhm.
Okay, so you can share it with us. You should have made the little stick figures, to represent you so you can put it on your presentation. Okay.
Can you
Yeah,
see
you can
my
share whenever you're ready, you can go ahead and share. Thank you.
can you see my slides?
We can see your slides, yes.
Okay, I will begin. Hello everyone, my name is Sorry Feng. Today I will present my work titled Material Point Strength Reduction Method and its application to slope engineering. This project is developed from topic 14. My presentation has 4 parts. Modern numerical simulation methods for slope stability, workflow of these methods, and case calculation, and finally conclusion. Firstly, I will briefly introduce several common numerical methods used for slope stability and analysis. The finite element method divide soil or rock into elements and nodes. It is widely used but may face mass distortion in large deformations. The discrete element method treats soil or rock as many individual particles or blocks. It is good for discontinuous behavior, but not ideal for continuous materials. The material point method combines the advantages of both. It uses the material points to store physical quantities and uses a background grid for solving equations. I summarized the comparison of the 3 methods in the table. And overall, the material point method can naturally simulate the entire failure process of a slope while avoiding mesh distortion, giving it a strong potential for future development. In recent years, it has received increasing attention in geotechnical engineering. Next, I want to introduce common ways to determine the slope safety factor. First, the strength reduction method. It reduces soil strength parameters until failure occurs. It is the most widely used method because it considers strength behavior. Next is the limited equilibrium method. It calculates safety factors using force and moment equilibrium. It doesn't consider deformation, but it's common in practice. The last is reliability-based methods, which use probability theory, but they require heavy computation. In this part, I will focus on explaining the principles of the material point-based strength reduction method. The core logic of the material point method can be summarized in 4 key steps. First, the material points are used to store physical quantities such as mass, strength, and strain. Second, a background computational grid is employed to solve the governing equations. Third, during each timestamp, information is mapped back and forth between the material points and the grid. Finally, by resetting the grid after each step, match distortion is avoided and the numerical stability is maintained. I think using some figures may help make this concept easier to understand. Simply put, the enhance of the material point method is to separate information storage from numerical computation, treating them as 2 independent components. These 2 parts then exchange information with information with each timestamp. Any distortion that occurs during the process is removed by resetting the computational grid at the end of every timestamp. The strength reduction method determines the factor of safety by gradually reducing the surge stress parameters of the soil or rock until the numerical model reaches a failure state. The reduction factor at the moment of failure is taken as the slope's safety factor. Usually, failure is identified by 3 indicators. First, a continuous plastic zone appears. Second, displacement increases suddenly, and last, the computation doesn't converge. This slide presents the overall workflow of this method. It includes strength reduction, grid particle mapping, solving equations, and updating particle states. The final output is the safety factor and the deformation pattern. The case is a landslide along the Yellow River. The slope is about 300 meters long and 200 meters high. The rock mass is highly weathered and divided into 3 layers, Group 1, Group 2, and Group 3. Rainfall is upheld at the top boundary, and the side and bottom boundaries are no-flow boundaries. Here are the results of the numerical simulation. These results show the internal strength distribution during slope deformation. And the plastic strain counters indicate that a continuous plastic zone develops from the middle to the bottom of the slope. This is consistent with the expanded failure model. The final reduction factor provides the safety factor of this slope. And to conclude, this method is effective for elevating slope stability. Compared with the finite element method, the failure criteria are more physically. However, it is still developing in geotechnical engineering. Its engineering applications are limited, and module software is still scarce. More research and improvement are needed. This is the reference. Thank you for listening.
Thank you. Does anyone have any questions?
I have a question.
Go ahead.
So this I understand correctly, was this implement or case study for the material point method for rock?
Uh, sorry. Uh, well, can you repeat again?
What was this? Is this like a rock slope?
No, it's a soil slope.
Oh, okay, sorry about that. No, okay. I mean, I was just confused because on the slide you said there's a rock mass is highly weathered. So what do we see in this cross section of soil 1, 2, and 3 if it's rock? And how, I guess how does material point method apply differently in rock versus soil, and how would you discretize it differently? How would you discretize rock different than soil?
Oh, I know. Uh, actually, this case is very, is very, uh, is very special. Because it looks like a rock, but it has a and 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 I think it is highly weathered, so its properties actually like soil. In this case, in this case, I think it's a soil, uh, a soil slope, and when I built the model, into three, uh, I divided it into three groups, and which group has different properties. So we enter the software div, so we enter the software with different parameters. So I think you asked how to discretize the soil and rock and rock and rock and rock and rock. I think we can use different pa pa parameters.
Constitutive model.
Yeah.
Thanks.
Any other questions? I will ask the same question that I asked before. Have you had the opportunity to compare the results from this method with a slope stability analysis of the same slope by conventional methods?
Oh, actually, I didn't compare, but I saw sorry. But I saw a particle about this que but but I saw uh I saw a paper about this question, and according his all and according to his all and according to his outcomes, the uh the uh the safe factors will small than the than the finite method.
Okay. Okay, thank you very much. I think we can conclude here. Unless someone else has another question, no? Well, thank you, everyone. Thank you for a great semester and your good presentations. A few presentations will be coming up in the next few days. I will be posting them in on Brightspace. Okay, for those who could not present tonight. But thank you for everyone who was able to make it tonight.
Thanks, Professor. I want to ask you questions. Actually.
Yes.
I mean, we have a lot of time. From all the topics, do you know how to do every topic?
Brush. I haven't looked at them in detail, right? So, but I have some idea of most of them. But they're not all. I mean, usually those topics are more things that we go into and specialize, right?
Yeah.
As
Yeah.
So that's why I was wondering because we have win-win. You did one method.
No. We it covers a wide range of topics, and you do it different ways. And but this is why you are here to instruct me too, right? So
Yeah.
every time I read one of your papers, I learn something.
So, based off of what I did, do you think that there's room to apply material point method? Because the more you guys talk about it, the more I'm curious about thinking of a way to apply it. But
Material point method is usually best used whenever you have a mechanical component. But that being said, whenever there is a mechanical component and there will be movement, right?
yeah,
Because material point method, in essence, is to map the movement of particles. It's to be
yeah,
able to deal with scenarios where you have large deformation. So you have these little particles. So whenever large movements can happen, then
yeah.
yes, you can apply the material point method.
So
Okay.
if I had a finite say some sort of finite difference fixed grid, and then I go through one thaw step and then one free step, and then I have a large strain. Do I would it be smart to apply material point method at the points in time where I do get the large strains, or
Uh, I'm not sure if it's convenient to only apply it at some point. It might be. I haven't looked at it in that way. I don't know what is more computationally intensive in the long run, right? If doing everything the same way all the time, or keeping another method in reserve, and then if you pass a certain strain, then you start applying it. I don't know. Maybe it is computationally less intensive. But at the same time, it does add an overhead, right?
yeah.
Because you have to do an extra check, and then once you decide to apply it, then you probably
Well,
have to
well,
apply it everywhere within your domain, because now things start moving. You
well,
will
the reason
have failure planes developing in some areas.
the reason I ask is because uh, what was I gonna say?
Actually,
Oh,
about the material point method, I want to share some of my experience.
Go ahead.
Actually, yeah, the reason why I choose this topic because I have 5 years work experience in China, and we have so many highway road, and aside with the highway road, there's a cliff, very high cliff, uh, on the both sides of the road, and the cliff has soil and the rocks, and we always put I don't know how to say in English. We call it the protection protection net to avoid the rocks suddenly throw down and like crash the cars.
yeah,
About this setting, we do not have any analysis method to design our protection net because we do not know the behavior of the rock fall out from the cliff. And I'm thinking about maybe the material point method have this
I
potential to solve
Yeah.
this problem.
Oh yeah.
Yes, I think so because material point method considers it's basically mass acceleration, right? So you're looking at and
Yeah.
you could have a block of, even if it's made of multiple particles, it could still be a free block that moves on its own that has the potential to break apart if need be, depending on how
Yes.
sophisticated you want to make it. But yes, it's probably the best way to kind of simulate. Probably you would have to combine the material point method with some sort of Monte Carlo analysis, right? Because
Oh,
so many things can change. What you would want to do is run like statistically multiple scenarios and then see what is the most likely outcome.
Yeah.
oh, okay, okay. Yeah, that's a good idea. That's a good idea.
So yeah, that kind of thing, because you don't know exactly what's going to happen. There can be so you include very small variations, right? You have the statistical variations of distribution of sizes, of positions, of et cetera, and then you run Monte Carlo analysis on it, and you see
Yeah,
what
yeah.
is the most likely outcome of all these random events.
Yeah, the highest probability of the behavior.
Yeah, yeah.
Is so is the software package Ram's Rockfall, is that material point method? Do you guys know about this software?
I am not
Actually,
familiar with that one.
actually, we have I do some research on this. I found there's a something called the 3D NPM software, but it's developed in China. I forget the name of the university, but it needs you to pay the money, so I
Yeah.
didn't try it.
Okay.
Yeah.
Interesting. Cool. Well,
Well,
I had
thank you,
fun.
everyone. It was an interesting conversation and discussion after the presentations, too.
Yeah. Yeah.
Thank
Yeah.
you. Yeah.
Well,
So, yeah, it was very pleasant experience this semester. So, thank you, everyone.
thank you.
And I hope the course has given you something to has added to your experience and knowledge.
Yep. Certainly
It's
has.
very helpful.
I'm glad then.
Appreciate it.
Have a good end of semester. If you have any exams, good luck in your exams, and we'll see you later.
All right. Take care.
Okay.
Thank
Thank
you.
you.
Thank you.
Bye.
Bye.
See you.